Let's take a look at an example problem here from Module 10.1 for ME 270 Structural Dynamics. So in this example problem here, they give us this diagram down below in Figure 1, which is a symmetric 2 degree of freedom spring mass system. So we've seen similar things like this before, but now we got two masses and we got three different springs in here. And they tell us to obtain the natural frequencies and the mode shapes of this 2 degree of freedom system shown in this figure. And they give us the equations of motion here. We have for M1, we have mu double dot 1 plus 2ku1 plus ku2 is equal to 0. And we also have for our second mass over here, mu2 double dot plus ku1 plus 2ku2 is equal to 0. So now that we've had an opportunity to read through our problem statement and take a look at our given diagram and wording of the problem, our next step is to create a setup page. So that's what we do here is we create this setup page here. And our given information we write down here. So they tell us our equations of motion. We have our mu1 double dot plus 2ku1 minus our ku2 is equal to 0. And we have our mu2 double dot minus our ku1 plus our 2ku2 is equal to 0 there. And they ask us to find our omega 1 and our omega 2. And I simply come down here and I redraw out a simplified version of my given diagram. I have my first mass here, my second mass over here. I have all three springs right here, K, K, and K for my spring constant values. And I have for the first mass here, displacement as U1. And for my second mass here, my displacement here as U2. So with all the information that we're given in the problem statement, now that we've got a nice spot to reference back to on our setup page, what we want to do now is take a look at what key equations are we going to utilize in order to solve this problem. So first thing we can do is we can assume harmonic solution. So if we assume the harmonic solution, we can go to equation 9.3 in our textbook. So this equation gives us the relationship that we see here. So we see here that u1 of t is equal to u1 times the cosine of our omega sub I t minus alpha, and u2 of t is equal to u2 times the cosine of our omega sub I t minus our alpha term there. So this means that when we have the 2 degree of freedom system vibrates at a natural frequency, omega sub I, then our u1 and our u2 displacements have the same dependence, and at all times, the amplitude, or our u2 over u1 is equal to our capital U1 over u2. So for the next portion of our solution, what we want to do is substitute the harmonic solutions equations into the given equations of motion at the beginning of the problem statement they give to us in order to get an algebraic eigenvalue problem. So here's our equations of motion. I rewrite those down. Here's our harmonic solutions right here. I write those down again. So we take a look at these and these right here. And again, the next step is to take the harmonic solutions and sub them into our given equations over here. So these are for u1 of t and u2 of t. So those we want to put back in to our equations of motion in order to get our algebraic eigenvalue problem. So the first thing that we should notice is as we go to plug in our harmonic solution into our equations of motion, what we notice is we have a u double dot term in both of our equations of motion for the mass 1 and for mass 2. Now, what we need to do from our harmonic solutions now then is take the second time derivative of each of those for u1 and for u2 in order to get the u1 double dot and u2 double dot to plug into our equations of motion. So we do that here. I've rewrote out my harmonic solution up here. I've taken the second time derivative of our harmonic solution for u1, so u1 double dot of t is equal to a negative u1 times my omega squared times the cosine of omega t. Now I do the same thing for u2 of t here, so u2 double dot of t is equal to a negative u2 times omega squared times the cosine of our omega t here. So now we have a values for omega, or for u1 double dot and u2 double dot that we can plug into our equations of motion here and here. So I've color coordinated this, and what I've done is I've written out my general solution for both equations of motion, and then down below here now I have plugged in my values now based off of my harmonic solution into those equations of motion. So we'll start with the top one for the first mass here. So this is m times our u1 double dot. So I have my u1 double dot right here, so this can come down and plug in right there. And then I have plus 2k times u1 Well, here's our u1 right up top here, so I can take this value down and plug it right here for u1. That's the same one we plug in for our mass 2 as well, right there. And then I have minus k u2. Well, here's my u2 value right there, so I can plug this down in right here for my u2, which is there and there as well for the second mass. The only difference here for my second equation of motion we can see is this circle here in my orange. So this is my u2 double dot, which from right up here, from taking that second time derivative, I can now take this and come down and plug it in right here into this second equation of motion there. So now I have both of these results as I've plugged my harmonic solution into my equations of motion. So now if we take a look in detail at this equation here that we just came up with by plugging in our characteristic equations into our equations of motion, we can see here, okay, I've got a u1 here, a u1 here, and a u2 here. And my second equation is down here. I've got a u2, a u1, and a u2 right there. So what we can do is we can start distributing through simplify and reduce. And when we simplify, reduce, and rearrange, we can realize that we can take this complicated equation for our equations of motions with the characteristic equations plug in and come down here now to a matrix form of this. This is going to make our lives a lot easier. And we do out our matrix form of this here. You can see there's our u1 and our u2 right there. Pull out our coefficients in front here once we've simplified and reduced, and end up with this version here for our equations of motions with those characteristic equations plugged in after we reduced and simplified and rearranged a little bit. So this makes a lot easier form for us to deal with. So now that we have the matrix form of our equations of motion, the next thing we want to do is set up our characteristic equation. In order to set up our characteristic equation, it makes life a little bit easier now that we have it in matrix form, because all we need to do is take the determinant of that coefficient matrix from our previous slide. So here we have that same matrix right here. And if we want to take the determinant of this matrix here, we can say this term times this term minus this term times this term is equal to 0. So we do that there, and we say this term here times this term here, minus this term here, times this term here. So we do that, and we end up with 2k minus m omega sub I squared from right here, times 2k minus m omega I squared from right here, minus negative k times negative k. Negative k times negative k. So this is where we really need to pay close attention to our sign convention. Our negative k times negative k gives us a positive value, but then we still have this negative here, which brings it back to a negative again. So now we can go through and FOIL this guy out, or realize it's just the same term here and just put a squared right there. So that's what I do, is just say, okay, it's this squared minus our k value squared is equal to 0. So we can still reduce and simplify that a little bit further, and when we do that, we can now see that we have m squared times my omega sub I squared minus 4k m omega I squared plus 3k squared is equal to 0. And we end up with this equation right here after we take the determinant of that matrix. So the next step in our solution is to factor in order to obtain the roots of our characteristic equation. So this is our characteristic equation right here that we solved for in our previous slide. So we have our m omega sub I squared minus k times m omega sub I squared minus 3k is equal to 0. So therefore, if we were to solve this out and find our roots of this equation, we'd find that we'd have an omega 1 and an omega 2 squared right there when we plug in. So our omega 1, our first root, is omega 1 squared is equal to k over m. Our second root, omega 2 squared, is equal to 3k over m. So I can solve this for omega 1 by taking the square root of both sides. So my omega 1 root here is equal to the square root of k over m, and our omega 2 is equal to the square root of 3k over m.